All right, my name is Philip Melo, and today we are going to talk about how to build a neural network. A neural network is a backbone of deep learning, artificial intelligence, and plays a very important role in various disciplines, including healthcare. And today our example will be on healthcare. So neurons are responsible for carrying information throughout the human body. So neurons send signals in our body everywhere when we go to human body. And actually, what happens is that neural network that we do, it's called artificial neural network, it mimics the neural systems in our body. So using electrical and chemical signals, neurons help coordinate all of the necessary functions of life. And nowadays, neural network actually also coordinates and defines that many areas of science and technologies and help build accurate algorithms for classification and the prediction of various events. And also business plays a very important role in healthcare. So it has been estimated there are around 86 billion neurons in our brain. Okay, so it's a huge network in our brain, but actually there is no also limit. There is no limit when we can do in terms of computer. Nowadays, computers are very strong, and using the strength of computer, we can build also quite reasonable, quite important in terms of applications, neural networks. So first of all, I'd like to say that we can see here. Let me just put here. We can see here the neuron and this kind of information that comes through the neuron and goes out as an output. So what happens here that this information x1 comes with some weight, and weight is a vital tuning operator that will help us to achieve high accuracy, and I will explain you how it works. So a neuron gets information as input and does some operation, for instance, summation of this information that it got from different neurons. For example, if we have an image of a cat, so this, for instance, X1 describes the ears of a cat, that this one legs, this is whiskers, and so forth. So we have a number of neurons that goes into this neuron with some weights. Okay, so the input comes to the neuron, and neuron does some operations and also goes output. This output can go, for example, for a next neuron, right? Like for instance, in deep learning, we have various these outputs that goes numerous outputs that go to other neurons and neurons and neurons and neurons that helps us to accurately estimate, for instance, some processes. So what happens is that this next input x2 comes with this. It also in signal processing it is like a filter, so it is multiplied by this filter, and it comes to this neuron, and neuron does some operations. So this is operation that happens inside neuron, and neuron also then is an output, send this information outside. Okay, so that's how it works. Now, when we talk about, let's say, a deep layer, we have input layer. Okay, so there are some neurons, not some, but maybe can be numerous neurons, right? And they are interconnected with the next layer, and this layer interconnected with another layer, and these layers are called hidden layers. Hidden layers. So this is input layer, output layer, and hidden layers. And hidden layers can be many. Okay, it depends on the problem. We also will talk about it. So, and you see that all this, for instance, this neuron gets input from this neuron from input, from this neuron, from this neuron, from this and this and so forth. Okay, that is also interconnected. Same thing as in brain we have. Now, what happens here is that we can see that also in our brain can be represented by these figures that you have various neurons and they are connected with other neurons and give some signal as an output that are absorbed by another neuron or it goes outside to cells. That's how it works. Now, I would like just to show you how we can build a neural network. It is a simple, straightforward procedure, and I'm sure that you will understand how to do it because it is quite simple. All right, so it is we can do it in one lesson, and you will be specialist in building neural networks. All right, so we have input. You see, I it is for input. I1 from this layer, input layer, I1 and I2. It is for simplicity, but it can be also I3 here, I4, and so forth. So imagine now that we have another neuron. This is H1, H2, and this corresponds, why it is H? It is hidden. This is I, it is input. H is hidden, so hidden layer. And we have only one, let's say, layer. It is just for simplicity. And this goes to the final output that will give information here. And this will, for instance, classify an object. So it will give you some result of this neural network. So this from I1, as I said, we multiply by W1, and this comes to H1. Okay. What we can do also, we will just not do just multiplication, but we can do using this function. And this function is called activation function. Activation function. It is important. So we have weights, W1, let's say, and that comes to H1. And from I2, it comes, we call it this W3. So this comes a input from neuron 1, neuron 2, and this is weights, W1, W3. And B is called bias. We will also tell you what does it mean, bias. Okay, and and this is activation function. Activation function plays a very important role because it can be 1. So if it is 1, it will just W1 times. So it is just straightforward. So it is not a function actually, right? But in neural networking, we apply many functions, okay, possible. Like reflu, we call it this function, sigmoid function. And imagine now, as a simple example, we will use an activation function. What does it mean, activation function? In this case, in activation function sigmoid, it is goes from 0 to 1. So from 1 to 0, from 0 to 1. This is sigmoid function. And as I said, the activation function depends on the problem we solve. And in this case, activation function is very important, okay, because activation function can be very close to 1 and very close to 0, right? So it is 0, 1. It is classification. For example, we can use it if it is close to 1, let's say in healthcare, person, let's say, has cancer. If it's close to 0, there is no cancer. So this is classification problems. For classification problems, I strongly recommend to use the sigmoid function. It is very handy, okay? And as you see from this formula, I will just rewrite it. Sigmoid function, sigma x, equals, as you see here, 1 over 1 plus e in the minus x power. So when x is high, goes, let's say, to infinity, it goes high. So this becomes 0, and you have 1 to 1, it is 0. 1 to 1, it becomes 1, because this becomes 0, right? But when x goes to infinity, so large values, and you see here from this graph, it is very fast goes to 1 and very fast goes to small numbers. So this number becomes 0, because when x goes to negative numbers, large becomes 0. And when x goes to goes to positive, it becomes very fast 0. It becomes 1 over 1. But x, when it is negative, then it becomes negative becomes positive, and this becomes a very large number, and it becomes to 0 when x takes negative values. Let's say it goes to negative infinity. So this becomes a very large number, and then it 1 over a large number becomes a very small number close to 0. So this is a very good activation function that we will use. Now, let's just make a very simple example. We can build neural network. So the input I1 is a glucose, for instance. Now we'd like to see whether a person has diabetes or not. So we take 146. And the body mass index, it is 34. BMI. So glucose 146, BMI 34. Let us make now assumption that we start with like iterations. We start with a simple example that all weights are 1 and all biases are 0. And I will just explain exactly what does it mean bias and weights when we will discuss how to estimate them. So just imagine that this is numbers that will take 1 and 0. Let's see what happens here. Okay, so we will put h1 in this formula because f, we know that is activation function. It is 1 divided by 1 plus exponent of x. In our case, it is I1, which is 146 at glucose, and also 34 is BMI. So we have this value in the argument of the exponential function. It becomes negative 180. 146 negative and negative 34 gives you 180. What happens here, and I strongly recommend you, there are many ways, because this one is a very small number, okay? Very small number, but also to calculate this number is a challenge. So I just urge you, when you build a neural network, to normalize the values, let's say in our case, glucose and BMI. When you do normalization, you will have glucose becomes 0.9 and BMI 0.2. So instead of this working with this number, which is, as I said, challenge to calculate, you will have a very simple value. It becomes 0.75. So I urge you to do normalization, and then you will have reasonable numbers for analysis. Now, when you put the H2, because W2 is 1 and W4 is 1, and B2 is 0, you will have the same thing as in H1. So H2 becomes 0.75. Okay, so now we calculate, so this is 0.75, 75, and this is 0.75, we should calculate now what we'll have in the output. So what happens here that with W5 is also our, we put as a first guess, it is 1 and 1, the first estimate. So we can calculate now outside what it is here, what will be as an output of these hidden layers. All right. So we will put this f, again, it is sigmoid function. This one is 1, this is 1 is 1, and B3, it is bias. We just put it as 0. Okay. So what happens is that when we calculate, you will have 0.82. So we have this number which will have as an output. So this is the result of our network. Okay, now what happens here? We will take a look at the more interesting example. And we will have here glucose 85, 26 as BMI, and this person doesn't have diabetes. And then a second patient, glucose 90, BMI 28, also doesn't have diabetes. And the third one, 107, 30, and 1, it has diabetes. And 137, fourth patient, 43 and 1, this person has diabetes. So what we have to do now is to build a neural network. Why? Because what we will do, we will have, let's say, another patient whose, for example, glucose is, let's say, 95, and the BMI, let's say, 29. And we should predict if this person has diabetes or doesn't have diabetes. So this is a classification problem. We have to classify this patient using neural network. And this is our data. We will use, it is very small, of course, example, we have a very small data set. We will use it as a training data set. So we'll train our network on this data, and we'll see how it's accurate for the patient who has glucose 95 and BMI 29, whether he has diabetes or doesn't have diabetes. Okay, so we will normalize again, as I said because otherwise it is difficult to calculate these small numbers when the exponent in power, let's say 300 or something negative. So normalization formula is this one. We take a value minus a minimum in this data set, let's say in glucose, and divide by maximum minus minimum. So we will have these values. Same thing we do for BMI, and we have these values. Now it is reasonable and easy to work with these data. So what we do, we, let's say, have to do before going any further, I would like to tell you what does it mean true value. Okay, so true value is this one. We train data, okay, and we take this example as a training data. We'll train our neural network, right? So this 0, it is true value. So this is true value. This is true value. This is true value. This is true value. Now, we also introduce another value, which is called y predicted. Okay, y predicted is that what our neural network will calculate. For example, instead of 0, it may give you, let's say, 0.63, let's say like this. So this is our predicted value. And this is what true value. And of course, the difference is large. Okay, so this is very inaccurate result. But our goal is to make IP, predicted value, very close to Y true. So we will try to do next to build a neural network that gives very accurate prediction or approximation of Y true. For example, it can be 1005, let's say. So it's very close to 0. So it will take a 0 when you do round off, right? So this is our goal. Okay, so make predicted value close to true values. All right. So what happens? We need to minimize the true minus yp predicted, and in that second degree. Why it is like that? Why it is important? Because when you just minimize, that students often ask this question: why we do not minimize yt minus yp? Okay. This is a question that students ask, why we need to minimize the difference in the second power. And here is the answer is very simple, because what does it mean? What is bigger, minus -5 or -10? Okay, so -10 is smaller than -5, right? So this -10 is smaller than -5, right? You remember that if I take this -5 and this is -10, -10 is smaller. Then I go to -20, it is smaller than -10. So this answer will be -infinity, right? Because when you minimize it, it's -infinity, so it goes to infinity. So therefore, we do not want this scenario when we put squared. So then it is, instead of all this negative, it will be we'll have always positive output, because, and this is called loss. So loss is always or 0 or positive number. Of course, we want to have 0. We want to have yt and yp very similar. So yp should approximate yt. Okay. Now, suppose we start with here. And what we start, we put, let's say, all our weights, so W1, W2, all kind of weights we can put here equals 1, as we did it in the previous example. You put 1, and all biases we put 0. Okay, so what happens is that if we have here, so suppose this will start here in the loss function. This is loss function. And then, for example, we change these parameters and we go here. Okay, it means that we are going wrong direction. Okay, because loss function becomes larger. So what we need to do, we need to go to this direction in this way that the loss function gets smaller and smaller and smaller, and finally we have this W star that minimizes loss function we have close to 0 value. So this one, that what the procedure, we need to minimize our weights and bias, so we come to this minimum. And this function actually is nothing else as a parabola. this second power, it is parabola. And this parabola has this graph. And of course, when we start this, our algorithm should change a little bit this value. We can go here or here. Of course, we have to choose this one scenario because this loss function becomes smaller. Okay, so the algorithm, our algorithm will will choose W, the procedure. It is called gradient descent in such a way that the loss function getting smaller and smaller comes to this minimum, and we have to find this W star. I promise you to also to explain what does it mean bias. So when we have, let's say, a function y equals mx plus b. So this is, let's say, a line. So this one is a slope of this line, and b is an intercept. So intercept is this one. This is b, and this angle is m. Okay, so tangent of this angle is m. So that is the idea of bias. So it's another parameter that specifies the information about this function. So it is intercept and m, because when you have, let's say, m, the same thing as parallel line, intercept or bias will be different. So it gives you complete information about this function, right? Sometimes in some textbooks, you can say that bias is W0 is called. So they also, instead of B, put W0, but it's the same thing. All right. So now you learned how to build a neural network. Okay. And so what you do, you take inputs, you normalize inputs, and you start with putting weights equals 1 and bias 0. And then you have output. Don't forget to do normalization. And then you have an output. But of course, we have no guarantee that this output is good, is accurate, because we have also to tune our W. So in this case, when we have line, so we need to adjust our slope, right, and adjust the bias to approximate, let's say, any curve, let's say, if you want to do some linear approximation, right? So what you have to do, you have to tune your slope and your intercept and to approximate a function, right? And the same thing as here. So what I will show you next lecture, that how we can do this approximation in the most optimal way. So we will do this approximation, I mean, this predicted value becomes closer to the true value. So our goal is to build an algorithm that will minimize the loss. So we will find the parameters W and bias, that YT becomes YP, and you will be we will be very happy to see how we start with, let's say, first approximation, first iteration with W1, and W21, and W31, and W451, but then we come to, after this algorithm that minimizes loss function, we will come very, very close to 0, 0, 1, 1. All right, so that was my lecture for today, and see you next time. Thank you.